molecular orbitals being slightly different than the atomic ones. So since really haven't had a whole lot of time to look at it, why don't we just do number one together here, just to show you sort of what, you know, I'm kind of looking for. And then you can look through and have a, see if there's anything that confuses you or you'd like to review together while we're all here. So we have, we're just talking about carbon right here. So we're looking at CO2. So it's CO2. If we draw CO2, and that's one of the further questions, we can just do it right here, because we know that CO2 only has two places where there's bonds, right? And it looks like this. So we have carbon in the middle, oxygen on one side, oxygen on the other side. And then the oxygen also has a couple of lone pairs. Now, whenever we talk about molecular shape and all that kind of stuff, we're basically asking, what does it look like around the central atom? That's the key to all of these sort of shape questions and hybridization questions and everything else. We're almost always asking about, what does the central atom do? Because the bonding of the central atom basically tells you what the shape of the overall molecule is going to be. So if we were to do the AXE here, and you remember this is how we determined what group of shapes that the molecule would be. A is what? Remember what A stood for?
Central atom.
The central atom, right, whatever it is. So that just tells us A. It should just be CXE, but you know, AXE, that's for ax. CSE to CXE isn't a word. But anyway, yeah, it just tells us to look at the central atom. So that's carbon. So when we look at carbon, what's the X stand for?
Surrounding atom.
Right, how many atoms are around it? And so for X, what will we put down here? So there's a number. Remember, we put a number after X and E. So what do we put down next to X? We put a little subscript by the X.
Would it be 2?
Yeah, exactly. There's 2 atoms around it, so we just put 2. Now, what does the E stand for?
The polar 1, 2, 3.
Sorry?
4 count?
Still couldn't hear you.
4?
4. Oh, what does the E stand for? The E. So A is the central atom. X is the number of atoms, of surrounding atoms, next to the central atom. And then E stands for something. What does E stand for?
Non-bonding valence electron group.
Right, basically lone pairs. How many lone pairs does the central atom have around it? So when we look at the carbon, how many lone pairs does it have?
Four?
So lone, it has 4 valence electrons. That is true. It has 4 valence electrons. It has 1. So 1, 2, 3, 4. Yes, it has 4 valence electrons. But are they in lone pairs or are they in bonds?
Bonds.
They're all in bonds, right? So it doesn't have any lone pairs. It only has 4 valence electrons, and each of them is being shared to make 4 bonds. So it has no lone pairs at all. So for E, what number do we put down?
0.
0. Doesn't have any. And so if you remember, and you can look this up, I'm going to post this. Someone mentioned it during office hours this morning. Remember, I made in the slides for chapter 5, I made a couple of basic. It was a guide to all the groupings based on AX2 and AX3 and AX3E1 and all that kind of stuff. You don't have to memorize that. So what I'm going to do is just post that on Canvas. You can just have it to immediately look at when you're doing tests or whatever, or things like this, because there's no reason to remember all those shapes and everything. But what this does, what this basically helps us do, is determine how many electron groups, how many regions of electron density are there around the central atom. And when we see AX2, which is true for this particular molecule, we can see that there's 2 regions of electron density. There's 2 bonds on one side of the carbon, and there's 2 bonds on the other side of the carbon. And remember, we don't care how many bonds there are. If they're in the same region, we consider that one region of electron density. It just means there's twice as many electrons there as there would be for a single bond. But they're in the same area. They're between the oxygen and the carbon. So we've got one region here and a second region there. So when we have 2 regions of electron density, what shape does that molecule take on?
Linear.
That's right, it's linear, because that's the way to get this region of electron density and this region of electron density. The maximum distance from each other is to put them in a line that keeps them far away, because if we bend them in one direction, they become closer. If we bend them in the other direction, they become closer. So we put them in a line that's as far away, that's as far apart as we can get them. So that makes this a linear molecule. So because it has 2 regions of electron density, what kind of hybridization are we going to need to do for carbon? You remember there's SP, there's SP2, and there's SP3. Those are the 3 hybridizations that are available to us with carbon. That it needs to make 2 regions of electron density. So which one, SP3, SP, or SP2? Which one is it going to make?
SP2.
2 regions. SP2, okay.
Or SP.
So when you have SP2, how many bonding regions is that going to be?
Oh, it should be a sphere, I think.
It should be one?
A sphere. The
A
answer.
sphere? No,
SP, the answer, not SP2.
No, but if it's SP2 hybridized, that means how many single bonds is it making? Here, why don't we fill in the electrons? So this is the unhybridized over here. We'll fill in the unhybridized electron orbitals for carbon first, and then we'll figure out what we have to do to make this. So how many valence electrons does carbon have? What group is a carbon in?
4.
4.
4, right. So it has how many valence electrons?
4.
4, exactly. So we're going to fill them in. So where do we start? So what energy level would this be anyway? So we're looking at the energy level here. Which energy level are we filling in? So N equals what? N, 1 or 2 or 3?
2.
This is 2, right? Because it has both a P, S, and a P. If it was level 1, it would just have S. If it was level 3, it would have S, P, and D. So this automatically tells us we're on level 2. And that's where carbon's valence electrons are. So it has 4 here, right? It has 4 valence electrons. That's the number of electrons in the outermost shell. That's the very definition of valence electrons. That's why on the test, when we asked how many valence electrons does oxygen have, what was the answer? You guys all took the test. You must remember, it was the very first question. How many valence electrons does oxygen have?
6.
6. And how many total electrons does oxygen have?
8.
So how many core electrons does it have?
2.
2.
2. That's right. It's whatever's the valence electrons or whatever's in the outermost shell, and the core electrons are everything else. And so just like oxygen, carbon only has 2 levels. So the first level just has 2 electrons in it and 1 s, and that's it. Those are the only core electrons it has. So let's fill in the 4 electrons that go in the outermost shell. Where's the first one go? So here we got 2p and 2s. Where does the first one go?
S.
Mm-hmm. Yep. And is it spinning up or spinning down?
Up.
Up. Yeah. Oops, somebody else got a doggy. Might actually be quiet right now. So there's the first one. So where's the second one go?
To 2p.
Do we go to 2p or do we fill in 2s or first?
2s first.
We fill in 2s first because we fill all the lower energies till then we move up to the higher one. So we put the second one in 2s, and which way is it spinning?
Down.
Down. Yeah, so now 2s is completely filled because every orbital could have a maximum of 2. Now, where do we go? Where's the third one go?
Goes up to 2p.
Mm-hmm. Now, is there any particular one of these we have to put it in? Can we put it in any of the 3?
No, we have to start from the left to right.
Yeah, we usually go from left to right, but honestly, we could put it anywhere because we didn't really talk about it much during the lecture, but we call these degenerate. I know it's a terrible thing to call them. Degenerate. And we call them degenerate because they're all the same energy. So realistically, it wouldn't really matter where we put it, but we normally just start from the left, right, just because it makes it easier on us. But truly, it doesn't really matter because they all have equal energy to each other. So we'll start from the left. So put the first one. So here we have -1, 0, +1. So where do we put the first? Where do we put the first one?
-1.
The far left. So we'll put it here. Going up or down?
Up.
Up. Okay. And where does the next one go?
0.
That's right. And what's direction?
Up.
Up. And we're done. That's 4. 1, 2, 3, 4. So we have four electrons. And those are our 4 valence electrons. So you remember, we have to hybridize these because we need 2 electrons to form single bonds, and we need another 2 to form double bonds. And they have to be of equivalent energy. And here we have these two s electrons that need to be part of the bonding process, but because they're sort of stuck together, they would have no reason to bond because that's a full orbital. So what are we going to do? We need some way that we can form hybrid orbitals so that two of them just have one electron in, and we have two orbitals left for double bonds. So what are we going to do? What sort of hybridization are we going to do? We're going to do SP, SP2, or SP3. So this would be 1s and 1p, 1s and 2p's, and 1s and 3p's. So we need, remember, we need two regions of electron density, 1, 2. And we're going to form two sigma bonds, right? So right over here we have 4 bonds total. The first one is always sigma, and that means electron density directly between the two. And the second one is always pi. So basically we need 2 orbitals to form sigma bonds. So which of these 3 hybridizations are we going to do?
Is it SP3?
So when we do sp3, how many hybrid orbitals do we make? Just count them. 1s and 3p. How many hybrid orbitals would that make?
3.
4. One of them is s, and 3 of them are p. So when we hybridize all of them, we end up with 4 orbitals. Oh, there go the doggies. We have 4 orbitals, each one with 1 electron, and each one making a single bond. So is that the situation we have here?
No.
No, we need to make 2 single bonds, right? We need to make 2 sigma bonds. So which hybridization are we going to do?
SP.
SP, that's right, because basically what the hybridization means is how many single bonds are you going to make? And lone pairs. So basically it says how many regions of electron density are you going to have? And so we have 1 region on this side. So there's our 1 region on the left side, and there's our other region on the right side. So we're going to have two regions of electron density. So we're going to do SP hybridization. So what does that mean? It means we're going to take one of the p orbitals and the s orbital, and we're going to make them equal energy, right? That's what the hybridization means. Basically, we're going to mix them together. So what does that look like? So we're going to take this 2s and one of these 2p's, and we'll mix them together. So the s and one of the p's will be gone and replaced by 2 new hybrid orbitals, both sp. And they'll be a little bit higher in energy than s, but lower energy than p. sp1 and sp2. Or just 2 sps. They're both sps. So that's a little confusing. They're both sp hybridals. And what do we have left? We still have 2p orbitals left, so we'll include those as well. 1, 2, so those are 2p. So we still have 4 orbitals, just like we did before, but instead of one of them being s and 3 of them being p, now we have 2 of them being sp and 2 of them being 2p, okay? So now let's put our 4 electrons in. So again, we have our 4, we still have 4 valence electrons. That hasn't changed. We just need to fill them in. So where do we start? Where does the first one go?
On SP.
Yep, this one right here. And spinning up or down?
Up.
Up. Where's the second one go?
The next SP.
That's right. And you may be saying, hey, wait a minute, I thought we were supposed to fill all of the, the lower energy orbitals first. Yes, but remember, these are equal energy. They're degenerate, just like the p orbitals are. They have exactly the same energy. And so we fill all of the orbitals halfway, and then we fill them in entirely, okay? So we have our first SP and our second SP. And remember, those are the only two that we hybridized. So where are the other two electrons?
Go up to 2B.
Yeah, they're both in the same place they always were. They're both in the 2p orbitals. One of them's here, and the other one's there. So they haven't changed. So we had two electrons both spinning up in separate orbitals of the three 2p orbitals. We had two electrons in separate orbitals both spinning up. That doesn't change because we haven't done anything with those orbitals. They have not changed at all. So we leave them out. The only hybridization that's taken place is between one of the p orbitals that didn't have an electron and the s orbital that had two. That's the hybridization that's taken place. So we split those two electrons that were in s, and we put them in one sp orbital and the other one in the other sp orbital. Now we look and see what happens. So here is our molecule again. What does this electron do? What bond is being formed with that electron? So oxygen comes in and it makes bonds with carbon. So we've got a sigma on top, we got two sigmas, and we got two pi's on the bottom. Where does this electron go? What bond does that electron form?
Can you repeat that? So sorry.
Oh, no problem. So we have two sp electrons, right, in two different orbitals. Which bonds do they form? So when oxygen comes in, so I'm going to change my color. So when the oxygen has its two valence electrons, we have oxygen on this side, oxygen on this side. So we have oxygen atoms going here, and here, and here, and here. Which bond represents this filled orbital? Sigma or pi?
Sigma.
Sigma, right. It's one of the sigma bonds. The hybridized orbitals always form sigma bonds. That's something important to remember. The hybridized orbitals always form sigma bonds, or if it's a lone pair, If we have a full hybrid orbital that already has two electrons in it, remember, if an orbital has two electrons in it, it's done. We can't put any more electrons in there. But if it's a hybrid orbital with only one electron in it, the other atom coming in is going to share an electron to that orbital and form a sigma bond. So this is sigma bond number 1, and this one is sigma bond number 2. Okay? Now, where do the pi bonds come from? So these are the sigma bonds here. Where do the pi bonds come from? Where are those electrons? We only got, what electrons do we have left?
The 2p.
Exactly. This pair of electrons forms a pi bond on one side, and this 2p pair forms the pi bond on that side. So something to remember, the hybrid orbitals always form single bonds. When we have single electrons in them, always, always, always form sigma bonds. And the reason for that, I mean, basically the only reason for forming these hybrid orbitals is to increase the ability of one atom to overlap an orbital with an incoming atom's electrons. That's the whole reason for forming them. Because if we didn't do that, they wouldn't overlap very well. And when orbitals don't overlap very well, we get weak bonds. So we form hybridized. So S doesn't overlap as well with an incoming electron as well as SP does, because that stretches out the orbital. We go from a sphere to having it stretch out on one side. So we have better overlap with the incoming electrons from oxygen. So the hybrid orbitals make sigma bonds because they're right in between the two atoms. Whereas pi bonds, if you remember, have electron density both above and below the sigma bonds. Because remember, p orbitals look like this. They go above and below, or in and out, or up and down, or side to side. So they have elongated orbitals as well, but above and below. And so it is not as direct an overlap. It's sort of like a side to side overlap. It doesn't directly go between like a sigma bond does. So this is what our hybridization chart would look like for carbon when it has 2 sigmas and 2 pi bonds. So we count the total number of regions of electron density, that's 2, and so it has to have 1 s and 1 p because it makes 2 sigma bonds, and the other 2 p electrons are left for pi bonds. Does that make sense to everybody? And it's a lot to take in, but hopefully it makes a little more sense than when I was babbling about it during the lecture class. You see how it works? I mean, oh, go ahead.
I just wanted to clarify, sigma bonds, they have high electron density, and then
In between, they have high electron density in between the two atoms.
okay,
So
and pi bonds don't.
right. So sigma bonds look like this. So if this was my carbon, and that's my oxygen, the sigma bonds would look like this. So this would be my sp orbital, and the oxygen would have a p orbital here, and they overlap very well. So we have high density in between. So that's a strong bond. Now the p bonds, the other p electron for oxygen would look like this. And the p, Cammy, and the other p orbital for carbon would look like that. So we have overlap above and overlap below, but it's side to side. It doesn't come in direct contact. So we have sort of region of density above and a region of density below, but it's not nearly as intense a collection of electrons as in this sigma. So a sigma bond is much stronger because the overlap is really, really tight. And a pi bond is weaker because the density is it's more diffuse. It's not as direct. Shall we do another one?
Yes.
Okay. All right. All right, let's look at, so in CO2, determine the hybridization for the oxygen atoms this time. So let's do the same thing for the oxygen atoms. So let's look at, so we'll do CO2 again. So remember, so we've, oxygen has how many valence electrons?
6.
6. So 1, 2, remember, you get half, for valence electrons, you get half of the electrons that are in bonds. Basically, we're assuming we share them equally. Tammy! Let's see. We have some idiot going up and down the street with a motorcycle, setting off all the dogs in the neighborhood. Right, so we have 6 electrons total. So here's 2. Where do the other 4 go?
For CO or CO2?
For oxygen. Now we're just looking at the oxygen by itself. So there's a total of 6 valence electrons. It's got 2 in bonds. So we have 4 electrons left. So where do we put them?
2 on top and 2 on the bottom.
Yeah, so basically they're lone pairs now, right? And these, so these would be these would be electrons that oxygen keeps for itself. So those belong to oxygen. It's not sharing them. So how many regions of electron density do we have around the oxygen? And notice I didn't say bonds. I said how many regions of electron density do we have around the oxygen? Basically, a region would be where we would find electrons. So how many places around the oxygen atom would we find electrons?
3.
3, exactly. Here's 1. Oops, that I just erased. Nice. So here's 1 right here. It's a double bond, but it's one region where we're going to find electrons. It's a region between the carbon and the oxygen where electrons are. There's 4 of them there, but it's a region. And the other 2 are what? Where are the other 2?
Up and down, above
Yeah, the lone pairs. There's 2 and there's 3. So there's 3 regions where we would find electrons. So since there's 3 regions where we would find electrons, what hybridization would we have for oxygen? sp, sp2, or sp3?
sp2.
That's right. Because we have 3 regions of electron density. So when we hybridize, basically what that means is we want those 3 regions of density to be as far away from each other as possible. So you remember when we do an sp hybridization, we have density on one side and we have density on the other side. That keeps the electrons far away. That makes it linear. When we have sp2, we have 1, 2, 3, and we put them in a triangle because that keeps those hybridized electrons as far away from each other as they possibly can. And when we have sp3, we make 4 regions, and the shape that keeps those electrons as far away from each other as they possibly can is the tetrahedral shape. But here, we've got 3 regions, and so we do sp2. 1, 2, 3 regions, and that keeps at 120-degree angles. So this oxygen would be planar. The 2 bonds would be in one plane, would be in one part of the plane. This lone pair would be in the other, and this lone pair would be in the other, and they'd be separated by about 120 degrees or so, okay? So we're going to do sp2 hybridization. So how does that work? So how many of these, well, first let's put in the, this is the unhybridized over here on the left. So again, we've got the unhybridized on this side. So let's put in the electrons for the unhybridized. So how many valence electrons for oxygen?
6.
8.
8 total. It wants to get 8 total when it's all, when it has all the bonds formed. Yes, everybody wants to get to 8. That's the magic number. Unless you're sulfur or phosphorus, then you can get more. But everyone wants to get at least 8, right? So, but it only has 6 to start with. It has 6 valence electrons because it's in group 6. So we're going to have to put 6 electrons in here. So again, where do we start? Where do we put them in? And again, this is level 2. So we have 2s and 2p. So where does the first electron go?
S.
Pointing up or down?
Up.
Yep. Where's the
Down.
second one?
Also S down.
That's right. And the next one?
B. Another up.
So -1, 0, +1. Where's the second one go?
0.
0, pointing up, right? And then, so that's 4. And then what about, where's the next one go?
+1 up.
5. And then the last one?
-1 down.
Right. So those are the 6 valence electrons for oxygen. And then when we learned atomic orbitals, we looked at this and we said, well, this explains why oxygen makes 2 bonds, because it has room to put an electron here and there's room to put an electron here. So it makes 2 bonds, and then it has 1, 2 lone pairs. And that made sense. But then when we start to learn about shapes, we learn, well, no, that doesn't make sense, because that would make the wrong shapes. And so then we realized there has to be some sort of hybridization for that to take place. And we figured out that would have to be 2 sp2 hybridization, because there's 3 regions of electron density where all these electrons are going to go. So what is that going to look like? How many s and how many p orbitals are going to be hybridized? So with sp, remember we hybridized 1 s and 1 p. With sp2, how many s and p orbitals are we going to hybridize?
4. 3.
Which 3 though? We have 3 p's and 1 s. So we're going to hybridize 3. Which 3 though? All the p's, or which? What are we going to hybridize? Basically, what combination of orbitals are we going to hybridize here? So we have 4 orbitals total. We have 1 s and we have 3 p's. So we have 4 total. Which 3 get hybridized? basically you have two choices. It's either the 1s and 2 of the p's, or it's all 3 p's. Those are basically your only two choices. Which one is it?
3 of the p's.
Well, think what we're trying to do when we do this is we're trying to make 3 new orbitals of equal energy. The 3 p's already have equal energy. And they can't make 3 bonds because there's 3 regions of electron density. We already have 2 electrons in one of them. So we need 3 new orbitals of equal density, of equal energy. And the only way to do that is to take one of the s and 2 of the p's. That's what sp2 means. It means 1 s orbital plus p2, 2 p orbitals. So we draw them like this. Whoops. Helps if we've got that selected. 1, 2, 3. And we call them all sp2. And notice I put the energies of them closer to p this time because there's the energy of 2 p orbitals plus 1 s. And so it's going to be a lot higher than s this time, but still lower than p. Like the average energy of an sp2 would be lower than p, but higher than s. And what do we have left? So there's only 1 orbital left. What orbital's left over? Then we have 4 orbitals on this side. We've only hybridized 3 of them, so there's 1 left we haven't done anything to.
P3?
Well, 2p. We're on level 2. Yeah, so we have 1 p orbital left over, 2p. So we have 2 sp2, and we have 3 of them, and we have 1 2p orbital left over. So we still have, so remember, after you do the hybridization, you're gonna have the exact same number of orbitals you had before. So over here we have 4 total, and over here we have 4 total. Same number of orbitals. We've just mixed the energies of some of them, okay? But the total number will be exactly the same. So we still, and the total number of electrons will be exactly the same too. We still have 6 of them. So let's start filling them in. So we need room for 6 electrons. Now we're going to be forming a single bond and a double bond. So that's important to remember. So where do our 6 electrons go? Where do we put the first one?
sp2.
Yep. So 1, and then remember they're all the same. So 1, 2, 3, 4, 5. But remember, we're going to be making 1 single bond and 1 double bond. So since we're doing that,
Go
we
up.
need to, right, we need to put one of them up in the P so we can make, this will be left empty for the single bond, for the sigma, and this will be left empty for the pi. So that's what our hybridized orbitals would look like. So where are our lone pairs? Remember, the oxygen is going to look like this. So there's two bonds and 2 lone pairs. Where are the lone pairs? Where would I find two orbitals, two filled orbitals on the right side?
To sp2, the first and second one.
Right, here. There's one lone pair, and there's the other one. And so the reason why it's hybridized is basically for the shape, because we want to separate this lone pair and this lone pair and this bonding pair as far away from each other as we can. And so that's what the hybridization allows us to do. It separates them as far apart as possible. And then this will make a pi bond with the carbon, with one of the, remember, because when we did carbon, it had two electrons in p orbitals. One of them is going to go here, and the other one's going to go to the other oxygen on the other side to make another pi bond. All right, so is everyone thoroughly confused now?
Yes.
All right, well, let's just clear this out. And let's say we're doing carbon for, let's say we're doing methane. Let's say we're doing CH4. Now we did carbon already, and when it's unhybridized, we had 1, 2, 3, 4. That's what it looked like. So let's just do for CH4. So that looks like this: 1, 2, 3, 4, with single bonds all the way around. So how many regions of electron density are around the carbon?
4.
4.
4. So when we hybridize this one, how many hybrid orbitals are we going to need?
4.
4. We're going to need 4 this time, because remember, that gets us those electrons as far away from each other as we can, and that's what makes the molecule stable. When they're as far away from each other as they can, you don't have them interacting, repelling each other. So we need 4 places to put them. So what's our hybridization going to be? SP, SP2, or SP3?
sp.
Now that's for 2 regions of electron density. Remember, we count the number of orbitals. 1, 2, that gives us 2 regions of electron density. We need 4 regions.
sp3.
SP3, right, we just count them. 1s, 3p, that's 4. So we need SP3 hybridization. Well, what does that mean? That means we want to hybridize one of the s's and all 3 of the p's. That's what that means. SP3 means all of them will be hybridized. There's only one s, but there's 3 p's. And so we're going to hybridize all of them together and form this. 1, 2, 3, 4. SP3 orbitals with all equal energy. Okay? So we still have the 4 electrons to put in. So where did we put them?
Just 1, 2, 3, 4, all up.
Yeah, all the way along. 1, 2, 3, 4. So that means when hydrogen comes in, and we have 4 hydrogens, each having 1 electron, it's going to put them 1, 2, 3, 4. Those are going to be the hydrogen electrons from the 4 hydrogens. So and remember, what kind of bonds do hybridized electrons make? Do they make sigma bonds or do they make pi bonds? Those are the only 2 kind of bonds we have.
Sigma.
They make sigma bonds. So how many sigma bonds is it going to make?
4.
4. 1, 2, 3, 4. Now they're hybridized. So each one of those hybridized electrons can be as far away from each other as possible. When you have 4 regions like that, you get that tetrahedral shape. That's what gives it tetrahedral. I can't spell. So that gives you the tetrahedral shape, because there's now each one of those electrons is really far away from each other to reduce the amount of electrons coming in contact with each other and repelling. It reduces repulsion. And it gives it gives 4 places for hydrogens to share its single electron. 1, 2, 3, 4. So it gives us, and they're all sigma bonds because they're all single bonds. That's the easiest way to remember whether it's sigma or pi. Single means sigma. You even got the first 3 letters are the same. First 2 letters anyway. So 4 sigma bonds, 4 single bonds. So we need 4 equal hybridized orbitals to put our electrons in. Okay? To make a little more sense now, hopefully?
Yeah. I just have a quick question.
Cool. Yeah.
When I want to do, like, when it's 1 electron by itself, it's just easy, just do sigma, correct? But when
Yeah, if it's just sharing 1 electron with another atom, it's automatically a sigma bond.
But if it is like there is different, if S field and the up level like B is just 2 and there is 1 space, then I have to use pi.
Sorry, I didn't make that up.
So the example that you showed before, not that one, the one before, we use pi because there is 1 field and the other one is alone, so we have to make balance, correct?
Oh, right, we were talking about the oxygen.
Yeah.
Yeah.
Just I want to like summarize what I learned.
Right. So with the oxygen, we had 1, 2, 3. So we had sp2 and P. And so the reason why we didn't just fill all of its 6 valence electrons like this is because that wouldn't make any bonds. Because basically we'd have 1, 2, 3 filled 1, 2, 3 filled orbitals and no bonds. So basically oxygen wouldn't react with anything because all of its valence electrons would be in filled orbitals. So we have to put one of them in this p orbital to allow the sp2 to make a sigma bond and this p orbital to make a pi bond. That's why one of them has to be promoted to p, or else it wouldn't make any bonds. So basically we count the number of bonds that it makes, and there has to be single electrons in orbitals for that to take place. Remember, because remember, if there's a single electron in an orbital, it's going to be sharing it with somebody to make a bond. And we determine what kind of bond it's going to make by where it is. If it's in a p orbital, it's going to make a pi bond, p for pi. And if it's in a sp orbital, it's going to make a sigma. So sigma S, you can think of that for sigma, and P, think of that for pi. Okay?
Thank you.
Yeah, no problem. So yeah, so have a look through. Oh, one other thing. There's one other cool thing that we can do. Let's do the loop. So we've done the Lewis structure of CO2 1,000 times. Let's do it for carbon monoxide, because the Lewis structure for carbon monoxide is kind of weird. So let's do that one. So it should be pretty easy just to draw the figure, right? It's just see, oh, that's not gonna work. Let's do a darker color than that. Let's just do black for right now. All right, so we have carbon, and we have oxygen. That's it, that's carbon monoxide. So, how many valence Well, we'll put a single bond there, because we always have a bond. So how many valence electrons total do we have?
10.
10, right, yeah, we have 4 for carbon, and we have 6 for oxygen, for a total of 10. And we've got 2 here, so we have 8 left to add. So where do we put them? It's a little tricky because usually we think we'll put them around the outside, right? Well, we only got 2 atoms. So generally in this situation, we start with the more electronegative one. So who's more electronegative, carbon or oxygen?
Oxygen.
Oxygen, a lot more electronegative. So let's start there. So 1, 2, 3, 4, 5, 6, and there's 2 left, 7, 8. Now, let's do charges. Now, remember, we need to figure out what's the formal charge on each one, and we want to reduce the formal charge as much as possible. Because we don't want to have like huge negative charges on one atom and huge positive charges on the other. We want to reduce that as much as we possibly can. So what's the formal charge on oxygen? How do we figure that out? How do we figure out formal charge? Do you remember? What is formal charge? It has to do with the number of electrons. So how do we figure that out?
You take the number of valence electron oxygen needs, and then you
Yep.
take the number of valence electron oxygen has.
That's right.
it'll
So we
give you
start
the formal charge.
exactly. So we start with the number. So how many valence? So we start with the number of valence electrons it should have. So how many electrons? How many valence electrons does oxygen normally have by itself?
6.
6. So we figure out the number of valence electrons it has by itself, which is 6. 6, and then we subtract from that the number of valence electrons it actually has in the molecule. So we take the number of valence electrons in the atom, we subtract the number of valence electrons in the molecule, and that gives us the formal charge. So it has 6 as an atom. How many does it have in the molecule?
7.
7, right? It's 2, 4, 6, and we give it the one that it's sharing with the other atom. So for formal charge, we assume they're shared equally. And the last question is oxidation number. And oxidation number is different. The difference, we figured out the same way, but we subtract the number, we give all the electrons to the more electronegative atom. So if we were to figure out the electronegativity number, the oxidation number for oxygen, we would give it both of these electrons. So we would give it 8. But since we're figuring out the formal charge, we only give it the number of electrons it actually is keeping close to itself. So we assume it's keeping all of its lone pairs and one of the electrons that it's sharing. And in this instance, it's 7. 2, 4, 6, 7. So we subtract 7, so we get -1. So in this particular situation, oxygen has a -1 charge. So -1 on oxygen. What about carbon? How many valence electrons should it have?
4.
4.
4. So 4 is an atom, and we subtract the number in the molecule. How many does it have in the molecule?
3.
3. So what's its charge?
+1.
+1. So now we have a molecule that has a positive charge on one and a negative charge on the other.
We'll
what are
do
we
a
gonna
double
do?
bond.
Right, we put a double bond in. So we take one of these lone pairs, it doesn't really matter which one, and we move it to the middle to make a double bond. So now, let's take these out. So we put the double bond here. Take away that. And so what's the formal charge on them now?
None. None.
Yeah, there's none. Yeah, there's no charge. There's no charge on oxygen because it now has 6 valence electrons. And there's no charge on carbon because it now has 4 valence electrons. But what do you notice about carbon that's weird? Something weird about carbon that we don't normally see.
Double bond.
No, carbon makes double bonds all the time.
Yeah.
Would it be the valence electron? Or the lone pair?
The lone pair. That is very strange for carbon. Carbon rarely has a lone pair to itself. And so it's one of the reasons that makes carbon monoxide poisonous, because when we breathe in CO2 or CO, let me erase some of this stuff. When we breathe in oxygen, oxygen looks like this, right? And so we breathe in oxygen and it binds to iron in our hemoglobin, makes what we call a coordinate bond. We haven't really talked about coordinate bonds, but it makes a coordinate bond with helium, with iron 2+. So it's attractive to iron 2+. When we breathe in carbon monoxide, this lone pair of electrons from carbon makes an even stronger interaction with iron. And it doesn't release from the, because what we want with this particular bond, we want it to form and break easily. So we breathe in oxygen, it forms a bond. We send this to cells so that it releases the oxygen to the cells for it to use. We want it to bind easily and then release easily. But when we have carbon monoxide there, it binds easily, but it doesn't release easily. And so basically, if you breathe too much carbon monoxide, all of the iron in your hemoglobin gets bound up with carbon monoxide and you suffocate, because there's no room for O2 to take over, because the carbon monoxide is stuck there for too long. That's why it's dangerous. And so, yeah, carbon very rarely has a lone pair, and carbon monoxide is one of those times when it does, and it's not good. Basically, it's bad news when carbon is a lone pair, because it makes it a lot more reactive than it normally is. So there you go. So that's for carbon monoxide. So what other question would you like to do? We have a bunch of time left over. You see, I had to get my biochemistry in there. I'm always trying to sneak it in.
Professor, I have a question.
Yeah.
Do you think you'll be able to post this video on YouTube? So then if we have questions about it on the next your office hours, we can ask?
Mm-hmm. Yeah, I mean, it's recording. I'll probably get it posted by, if not tomorrow, then the day after.
Yeah, so then I think I have some questions about it
Okay.
during your office hours.
Sure. No problem.
Can we do question 4?
Let's have a look at 4. Which one's 4? Oh, so just let me take you through what I'm looking for in this one. Basically, there are atoms in here that don't have enough either electrons or bonds. So I just want you to fill them in. Like for instance, this carbon has only 3 bonds, and we know it should have 4. This carbon only has 3 bonds, and we know it should have 4. So fill in the bonds, fill in the lone pairs, and then the angles. When it asks you for an angle of 3, it would be like that carbon oxygen angle. What would that angle be around the carbon?
180.
And then, yeah, close. Well, either it'd be more or less. Basically, for the bond angle, what I'm looking for is it going to be more than 120, or is it going to be less than 120, based on the whatever structure you come up
Based
with.
on the lone pair too, right?
Yes, exactly. Based on the low pairs and the double bonds. So is this number 4? Is that the question you were looking for?
Yeah.
Okay, yeah. So this is vitamin B2, riboflavin. Now in this one, all of the bonds are present. So you don't have to add anything. Basically, it's asking you how many single bonds, how many double bonds, and fill in the lone pairs for the carbons, nitrogens, and oxygens to tell you what their hybridizations are. So if there's 2, wait a minute. If there's 2 regions of electron density, it would be sp. If there's 3 regions, it would be sp2. And if there's 4 regions, it would be sp3. So I'll show you a couple, and then you can fill in the rest, okay? So basically all of the oxygens present are going to have 2 bonds and 2 lone pairs, right? Because that's basically what oxygen does. Oxygen almost always looks like this. Oh, wait a minute, let me make that a little fatter so you can see it. Oxygen almost always looks like this. 2 bonds either on either side or on the same side, and 2 lone pairs. So let's look at this oxygen here. 1, 2, 3, 4. What would the hybridization of that oxygen there be? How many regions of electron density does it have?
Would it be 4?
4, right. It's 2 lone pairs, so that's 2, and it is 2 bonds. It's 2 more, so it is 4. So what hybridization would it be?
3 sp3.
sp3, right. So that would be an example of an sp3 oxygen. And now that would be different from this oxygen here. Now this oxygen down here also has 2 bonds and 2 lone pairs. So we would say, oh, it must be sp3 as well. But remember, the double bond is 1 electron group. It's 1 electron region because it's between the oxygen and the carbon. So how many regions of electron density does that oxygen have?
3.
3, right. It's got the
Would
lone
it be
pair.
sp2?
Exactly. Man, you're way ahead of me. Yeah, it's got 3. It's got 1 here, 1 there. Those are 2 regions, and this third region is the double bond. 3 regions means sp2. So basically, any oxygen with 2 single bonds is going to be sp3 because the single bonds are going to be at opposite sides. And if it has a double bond, that means it has 3 regions of electron density, and it's going to be sp2. Okay? So the quick way to sort of get through this is oxygen is going to have 2 bonds and 2 pairs. Nitrogen is going to have how many bonds and how many lone pairs typically? Oops. Undo. First of all, how many valence electrons does nitrogen have?
6 or 5, sorry.
5, right. And so when we do, so let's just do the Lewis dot diagram. 1, 2, 3, 4, 5. So basically this tells us it's going to have a lone pair and 1, 2, 3 bonds. So typically it's going to be sp3 hybridized as well because it has 1, 2, 3, 4 regions of electron density, except if it has a double bond. And carbon is 1, 2, 3, 4. So it usually has 4 bonds and no lone pairs. So basically, let's do a couple of the nitrogens. Let's look at the nitrogens. So let's look
Professor,
at this.
I have a quick question.
Oh, sure.
If you were to draw sp2 electron configuration, or not electron, is it orbital? How would you finish the s orbital and then the p would just be 2 arrows pointing up?
It depends how many valence electrons there are. If we're doing sp2 for oxygen, it would be 1, 2, 3 sp2, and there'd be 1 p left over, and 6 electrons. 1, 2, 3, 4, 5, 6. So it would make 1 single bond and 1 sigma bond and 1 pi. Yeah, we did that one earlier for CO2.
Okay.
But let's look at nitrogen right now, because there's 2 different kinds of nitrogens here. So let me erase some of this stuff. Let's look at the 2 different forms of nitrogen we're going to have. Some of the nitrogens are going to be all single bonds, and some are going to have doubles in them. So let's look at one that has a single, one that has a double. So here we have this nitrogen. That damn it. Here we go. That nitrogen there has all single bonds, right? So if it has 3 single bonds, what does it have, a lone pair or not?
Yes, at the bottom.
Yeah, it should. It should have a lone pair there. Because nitrogen has 5 valence electrons. So it needs 5 to be not charged. So 3 of them come from bonds. That's 1, 2, 3 valence electrons. And then the other 2 would be the lone pair. So in that instance, when it looks like this, 1, 2, 3, lone pair, how many regions of electron density does it have?
4 regions. So
4
sp3.
regions. So it would be sp3 hybridized. Right. Now let's look at, and that would be the same with this hydrogen, or this nitrogen here. That also has 1, 2, 3 bonds, and we put a lone pair there. But this one's different. Let's erase. We have a nitrogen here that's different. This nitrogen's different. Oh, I keep forgetting. Here we go. That nitrogen there is different because it also has 3 bonds, but one of them is a double bond. So it has 3 bonds, and we're still going to give it the lone pair that it needs for the 5 electrons. But notice it this time. This time, it looks like this. Doesn't look like that
So it's
anymore.
3 regions.
Exactly. So now it looks like this. And that's different because now we've moved a pair of electrons from here, and we've moved them there. So instead of having 4 regions, now we've only got 3. because that double bond is on one side, the single bond's on the other side, and our lone pair is up on top. So now we've only got three regions, 1, 2, 3. So because it has 3 regions, what hybridization does it have this time?
sp2.
That's right. So now it's only sp. Before it was sp3. Now it's sp2. Yeah. So just think of it. The number of electron regions is equal to the number of orbitals we're going to have to hybridize. That's how it goes. If it has 3 regions, we're going to need 3 orbitals. If it has 4 regions, we're going to need 4. If there's only 2 regions, we're going to need 2. And so the other thing that does, since we have 3 hybridized orbitals, we have 1 p orbital left over to make our pi bond. That one's the sigma, that one's the pi. We need a p orbital, we need an electron and a p orbital left over. We can't hybridize them all. We need a p orbital left over to make the double bond, to make the pi bond. So basically just go through and put lone pairs on the oxygens and the nitrogens. Leave the carbons alone. The carbons aren't going to have any. We check all the carbons, make sure they have 4 bonds. Pretty sure they're all going to have 4 bonds, and no lone pairs. Put the lone pairs on the nitrogens and the oxygens, and basically see if they have double bonds, they're going to have 3 regions of density, and if they have all single bonds, they're going to have 4. Okay. And same with the carbons. If it has 4 regions, it's going to be sp3. If it has 3 regions, sp2. And if it has only 2 regions, it's going to be sp. I don't think it has any, I don't see any carbons that have double bonds on both sides.
So in this question, I just have to count how many carbon I found in situation is
Yeah, basically just put lone pairs on everybody and just count them up.
Okay.
Yeah. Okay.
Okay.
All right, let's look at them. So this one would be fairly straightforward. Basically, you just use AXE for this one. So you look at SF6, S goes in the middle, surrounded by fluorine. So there's 6 bonds, and there's no lone pairs, so we know that's AX6. And we just look up what AX6 is. That's octahedral. It even tells you the shape. And you just have to figure out what the hybridization is. How do we make 6? Well, let's just answer the question. How would we make 6 electrons for making bonds? How do we make 6 sigma bonds? And how does sulfur do that? I thought our limit was 4.
Or double.
Isn't sulfur greater in the group number as it's going down?
Sulfur, yes, sulfur is in the 3rd period. And so sulfur has access to S, P, and D orbitals because it's in the 3rd period. Remember, every time we add a new period, we add a new shell. And every time we add a new shell, we add a new subshell. And so for level 3, we now have 3 subshells, S, P, and D. And so sulfur can put a lot more electrons than just 8 in there. So it can put, if it makes 6 bonds, how many total electrons is that? Total.
12.
12. Yeah, it can fit 12 in its outer shell. It's big. So how does it do that? It needs to hybridize. In order to get 6, you need to have 6 unpaired electrons of all equal energy to make 6 sigma bonds. And remember, sigma bonds come from hybridized orbitals. So instead of having 4 hybridized orbitals, 4, we have 6. How do we make 6 hybridized orbitals? We have our S, we have 1 S, we have 3 P, that's only 4. Where do the other orbitals come from?
Would it be D2?
That's right. So we have our 1s, our 3p, and 2d. So we'd say sp3d2 is our hybridization. And just count the number of orbitals you need. S has 1, p has 3, we need 2 more. We get them from d. 1 plus 3 plus 2 is 6, which is the number of bonds that it makes. Single bonds. Those are all single bonds.
Sigma?
Sigma and sigma, single, bleh. Yes, 6 single bonds means 6 sigma bonds. And since they're all sigma bonds, we need 6 hybridized orbitals to make them. Yeah,
So, Professor, quick question.
yes.
When we're doing the hybridization, so we're counting each valence electron, and then from there, that's when we get the hybridization.
Yeah, the hybridization comes from how many regions of electron density they're going to be. And in this instance, SF6, we count both the bonds and the lone pairs. And so there's 6 bonds and no lone pairs. That means there's going to be 6 regions of electron density, 6 equal regions of electron density. Since that's the case, we need 6 hybrid orbitals to deal with them. When we go down to NH3, we have 3 bonds and 1 lone pair. So we have a total of 4 regions of electron density. So in that instance, how many hybridized orbitals do we need?
8. You said you have 4 regions?
4 regions, yep.
6. Oh,
Nope.
hold on.
4?
4, we need 1 for each region. Yes, we need 1 for each region. So that would be sp3. So remember the shape of ammonia. We've got N, we've got our lone pair, and 3 hydrogens around it. 1, 2, 3. So it forms a tetrahedral shape because the lone pair is a region of electron density, just like these 1, 2, 3 bonds are. So if we have 4 regions of density, it forms a tetrahedral shape. And we get the tetrahedral shape from sp3. So we count the number of regions of electrons to figure out what our hybridization is. The number of sigma bonds formed will be the, basically you have to look at the structure. SF6 means there's 6 fluorines around it. So each one is 1 bond, that's 6 sigma bonds. CO2 has 2 bonds, but only 2 of them are going to be sigma, and the other 2 are going to be pi. So 2 regions means sp. It also means sp means 2 sigma bonds as well. So you can figure, you can figure this out, either way. How many total electron density areas are there? Will be equal. Well, just use that method. That's the number of electron regions will tell you what hybridization you need.
So, Professor, I have a question. So, for SF4, would it be sp3d?
Yes, exactly.
So I have a question.
Well, let's real quickly draw that to see what that would look like, and then hopefully that'll make a little more sense. So if we were to draw that, so we'd have S in the middle, and 1, 2, 3, 4 fluorines around it. 1, 2, 3, 4. And then, so how many valence electrons does sulfur have?
6.
6. So it would have a lone pair left over, right? So it's got 1, 2, 3, 4 valence electrons from the 4 sigma bonds that it makes, and it has another lone pair left over. So that's 5 regions of electron density. So if it has 5 regions of electron density, it needs 5 hybridized orbitals, right? So that would be S would be 1, and then our P3 would be 4, and then we need 1 more. So sp3d, that would be our hybridized orbitals for SF4. You have to take into account the lone pairs as well. All right. Why don't we do one of the oxidation number questions? Just because we didn't really discuss it a lot in class. We went over it briefly. I think I'd do like I'll do 2 of the really hard ones.
C.
Yeah, B and C are fairly, well, B you've seen before. You know how to draw phosphate. C you haven't seen before. So yeah, we'll do that one together. That's called thiosulfate. That's the thiosulfate ion. So yeah, let's do that one. Well, first let's just do phosphate because we know how to do that one. So P in the middle, 1, 2, 3 oxygens, 1, 2, 3. And so how many valence electrons on phosphate? Phosphorus.
5.
5. And it's got 3 oxygens. How many is that? How many valence electrons does oxygen have?
6.
6. And that's a total of 18, 23. Am I missing anything? Oh, 4, duh, sorry. 4, duh, man, idiot. So 4 times 6, 24. So 29 electrons. And am I missing any? Am I missing any electrons from this structure?
The phosphorus needs 1.
Plus 3.
Well, phosphorus has 5. Yes, the 3, the charge. Always remember, if there's a charge on it, we either add or subtract electrons, because that's what it means. It means it either has extra electrons or it has fewer electrons. If it had a positive charge, we'd have to take one of those electrons away. If it has a negative charge, it means there's 3 more than it usually has. So it has a net charge of -3. So we add 3 more electrons for a total of 32. So remember, we go all the way around. So we have 32 to put on it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And what have I missed? That's 24. I should have 32. But what electrons am I forgetting about?
The shared electrons.
The shared electrons, the ones in the bonds. Exactly. How many electrons are in the bonds?
8.
8. So I'm done. That's all of them. That's all 32, either in bonds or in lone pairs. So basically I'm done with. So now I look for charges. First I'll see what the formal charges are, and then we'll do the oxidation numbers, okay? So because they're very closely related. So remember how we did formal charges. We figured out how many valence electrons does it have as an atom, and then how many valence electrons does it have as in the molecule. So how many valence electrons does oxygen have as an atom?
6.
6, right. Oops. It has 6. And how many, and then we subtract how many it has as in the molecule. How many do they have as, and they're all the same right now. How many do they have as a molecule?
7.
7, right. Because it gets to keep one of those electrons that it's sharing for a total of 7. It's got the 3 lone pairs and 1 that it's sharing, so that's 7. So the charge on the electrons is on the electrons is going to be -1. They're all going to be -1. Now, what about phosphorus? How many valence electrons does it have?
5. But it
5. And how many does it have in this particular structure? In the
4.
4.
4, right, it only has 4. So it's, then remember, this is formal charge. So the formal charge of all the oxygens is going to be -1, -1, -1. And the phosphorus is going to be +1. And so when we see that in a structure, what do we normally do? To reduce the
Double
total
bond
number
it.
of charges. Exactly. So let's move this here. Make a double bond, and we subtract these 2 electrons. And so remember, this is like one of the questions from a previous, where you had to show all the resonance forms. So the resonance forms were basically either this oxygen has the double bond, or that one does, or this one does, or this one does. Those were the 4 resonance forms. So now we're done. So now we've gotten rid of this negative charge. Oops. We've gotten rid of the negative charge in this one. We've gotten rid of the positive charge on phosphorus. And so let's count up our net charge. So our net charge still has to be the same as the charge of the ion. And it's -3, right? We have three oxygens with negative charges, and that's it. So it adds up to -1, -2, -3. And that's what the overall ion has, that charge. So that works. Now let's figure out what the oxidation numbers would be. And we do that the same way. We figure out how many valence electrons, how many valence electrons does each have. The difference is if 2 atoms have different electronegativities, we give all of the shared electrons to the atom with the higher electronegativity. So there's 3 oxygens that have 6 electrons each, right? And a pair. They each have a pair of electrons that they're sharing. Now, who has a higher electronegativity, phosphorus or oxygen?
Oxygen?
Oxygen does. Oxygen has a higher electronegativity than everybody except fluorine. So basically, that's why we call it oxidation numbers, and we call it reduction and oxidation. Because oxygen is so damn electronegative, it basically steals electrons from everybody. And that's what it's going to do here. So instead of oxygen being nice and sharing this pair of electrons, it gets both of them. So they both go to oxygen. Now, how many valence electrons does it have?
8.
It has 8 now. All of those oxygens with a single bond all have 8 electrons now, because it's taking all of the shared electrons. So they all have an oxidation number of -2. Now let's look at this one. Let's look at this oxygen. How many, so you get to keep the lone pairs, so it already has 4. How many electrons is it sharing with phosphorus?
4.
4. And how many does it get to keep?
4.
All of them. So it also is an oxidation number of -2. So basically, all of the oxygens have the same oxidation number, regardless of the number of bonds they're making, because even the bonding electrons they get to keep because of their higher electronegativity. So all the oxygens are -2. Now let's look at what the oxidation number of poor phosphorus is going to be. How many? It has 5 valence electrons when it started. And how many valence electrons does it have now? If they all went to oxygen. So this pair went to this oxygen, this pair went to that one, this pair went to that one, and those 2 pairs went to that one. How many valence electrons does it have left?
0.
None. It doesn't have, poor thing doesn't have any. So what's its oxidation number?
0. Oh, 5.
+5. Basically what that means is that when phosphorus was by itself just hanging out as an atom having a good time, it got to claim 5 electrons for itself. Then when it gets bound up with oxygen, oxygen steals all of its electrons. And so it gets, we say it gets oxidized. That's what oxidized means, is that your oxidation number changes, it goes up. So either it was negative and now it's less negative, or it was 0 and now it's positive, or it was or you had, it was 0 before because you had the right number of valence electrons. You're supposed to have 5, you have 5, so your oxidation number is 0. Now it's +5. So the other way to check to make sure you got these right is when you add all the oxidation numbers together, they should equal the charge as well, okay? So this time, when we add up all the oxygens, what do we get? What oxidation number do we get when we add them all together?
-3.
-8. So we have 4 -2, so that's -8. And we've got +5 for phosphorus, so we add them together, -3. So we get the same number. So the only difference between oxidation numbers and formal charges are that the more electronegative element gets to keep everything when we talk about oxidation numbers, because that's really what we're talking about when we say something's been oxidized. It means that electrons that had normally got to keep close to itself are now going away from it and closer to somebody else, closer to fluorine or oxygen or nitrogen. Generally, it's those 3 that do most of the oxidizing. Okay? Do you see how that works?
Yeah, wait, Professor, so how did you get the 8 again? Can you explain again? So I know you got 4 from because
How do we get the -8?
yeah. I
Oh,
know
the
how
minus. Oh, okay, go ahead.
yeah, I understand the second part of how you got 4, but I don't know the first.
How we got, so you're asking where the -8 comes from?
Yeah, basically, yeah.
Okay, yeah, so we calculated that the oxygens with a single bond had an oxidation number of -2. You remember that? Because they had 6 electrons, it's 6 electrons in lone pairs that they got to keep, and there was a single bond, and they got to keep both of those for a total of 8 electrons. Well, that's 2 more than they're supposed to have. So that gave them an oxidation number of -2. And then we looked at the double bonded oxygen. It has 2 lone pairs for a total of 4 electrons, and it's sharing another 4 electrons with phosphorus. But it gets to keep all 4 of those that it's sharing as well. So it also has 8 total electrons. So its oxidation number is also -2. Because really it doesn't matter how many bonds you're forming if you get to keep all the lone pairs and all the bonded electrons. Basically, it's the total number of electrons around you. You get to keep them all if you're more electronegative. So if it's a single bond, a double bond, a triple bond, it doesn't matter. You're keeping all of them. So every oxygen had an oxidation number of -2. So in order to figure out if we have the right oxidation numbers for everybody, we add them all together. So we had 4 oxygens, all with -2 times -2, and that gave us a total of -8 for the oxygens. And then we added the number for phosphorus, which is +5, -8 and +5, that gives us a net charge of -3, which is the charge on phosphorus. So that tells us we probably did that right. The formal charge should add up to the right charge, and the total oxidation numbers should add up to the same charge as well.
Okay, thank you.
Got it? Okay, good. All right, we'll do thiosulfate and we'll call it a day. See if I can remember how to do this. It's been a while. So S2O3, I believe it goes together like this. 1, 2, 3. So how many valence? Actually, I should double check that. It's been I'm a little rusty with these. First of all, let's just count the total number of electrons we're going to need, valence electrons. How many valence electrons does oxygen have, and how many valence electrons does sulfur have?
Oxygen is 6.
Sulfur is also 6.
Right, they all have 6. Make sure I got my. Where's my thiosulfate? Sulfate 358. I think this is it. Yeah, so they all have 6. So how many total electrons are we going to need?
32.
6 times 1, 2, 3, 4. 32, right. Man, you've got ahead of me. You guys are getting too smart for your own good. Yeah, so 30 total for the atoms plus another 2 for the charge. So a total of 32. So 1, 2, 3, 4. Whoop. Let me just. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that's 20. And how many bonds do we have in, how many do we have in bonds?
7.
4.
So 2, 4, 6, 8. So we got 8. So we need a total of 24. And how many have I put so far? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I got 2 more to do. So let's put them here. Doesn't really matter where you put them. Okay, I think that's the total. Should be 32 electrons. Now, let's do our formal charges to see, because we might need to make some double bonds in order to get everybody chill. So this oxygen here. So we all know, so the sulfurs and the oxygens all need to have 6 valence electrons. So how many valence electrons does that particular oxygen have?
7.
7, right. So that would have a charge of -1. So we got a -1 there. And this oxygen is the same, the one right next to it. So that also has a -1. And what about this oxygen down here? What's going to be the charge on that one?
+1.
+1, right? It only because it has should have 6, but it only has 5. There's the 2 electrons, there's 2 pairs of electrons to itself, and a single one there. So that's +1. So that's problematic. Let's do the sulfurs. So again, sulfur should have 6. So how many on this sulfur?
6.
6. So that one's cool. That one has no charge. So that one's fine. And what about this one?
5.
That has 5, right? So that's +1. So that's a little problematic. So how are we going to, what do we do when we have negative, and do our negative charges work out? I think I'm missing a pair of electrons because I have 2 positive charges and 2 negative charges, and I should have 2 more electrons. So I'm just going to quick count these all again because I think I may have missed a pair. So 2, 4, 6, 8 there. 2, 4, 6 there. 2, 4, 2, 4, 6 there. Not that, no, that's a confusing way of doing it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I think I'm missing a pair. Can someone count these for me? I'm obviously having trouble counting them. 2, 4, 6, 8, 10, 12, 14, 16. I'll just count the singles first. 2, 4, 6, 8, 10, 12, 14, 16.
I'm missing one pair.
22. Yeah, I'm missing 2. Yeah, I thought so. Yeah, I'm missing 2 here. Yeah, that positively charged oxygen should have told me that there's something screwy. Right, so that goes from having a positive charge to having a negative charge. Now, I think now we're cooking. Yeah, you can see how confusing these are. Drawing these, you get lost sometimes. Right, so now we have a negative charge in that oxygen. That makes a lot more sense. Okay, so now we have 1 positive charge and 3 negative charges. So -2. That's good, that makes sense. Okay, so we're on the right track. So we have, sulfur's got a positive charge here, and it's surrounded by 2 oxygens, both with negative charges. So what do we do in that situation?
Double bond.
Yeah, do a double bond. So let's say these 2 electrons go to the middle and make a double. So we'll put a double bond there, and we'll take away those 2 electrons. So take these 2. Now the oxygen's no longer charged. What's the charge on that oxygen now? How many valence electrons does it have? As an atom, 6. How many does it have in that molecule?
4.
It has 4 in lone pairs,
6.
but it's sharing 2, right? So now there's actually no charge on it. There's no charge in that oxygen. What about the sulfur? It was +1. What is it now?
No charge.
Right. Because it has it has 4 bonds that it's sharing with sulfurs and oxygens. There's 4 bonds. So that's 4, and it has a lone pair for 6. So now there's no charge on the sulfur as well. And then the other sulfur doesn't have a charge either, right? Because it has 4 in lone pairs and 2 bonds for a total of 6, so it's good too. So this is a good structure we have. Looks like we have sulfur's violating the octet rule, right? You notice that the sulfur on the right is violating the octet rule. How many total electrons does it have? It has 6 valence electrons, but how many total electrons? does it have in its outer
12.
shell?
12.
Right. Well, 10 actually. It's got the 8 that it's sharing, and it's got 2 more for itself. So it's got 10. But that's fine because remember, it's in the third period. It has S, P, and D. It has extra orbitals to put those extra electrons in. So it has more electrons than 8, but it still doesn't have a charge because only 6 of them are valence electrons. So that's fine. So now, so we know what all the formal charges are, and they add up to what we should have, right? We have minus 1 in this oxygen. We have minus 1 in this oxygen. We have minus 1 in that oxygen, and no other charges. So the total charge is minus 2. So we're good. We're good with formal charges. That makes sense. Now remember, our oxidation numbers have to add up to the same, have to add up to minus 2 as well. So let's do that. So we can just go back and we figure out how many of the shared electrons does each atom get to keep, okay? So let's go one by one. So this one, this oxygen right here, how many valence electrons does it get to keep?
8.
Gets to keep 8, right? It has 6 to itself and these 2. So it is 8. And what about this one?
They're all 8.
Also 8. And this oxygen, 8. Now, the sulfur is going to be a little trickier. How many of the sulfur is going to get to keep for itself?
None.
No. If they both have lone pairs, they get to keep. This sulfur has the lone pair, it gets to keep those. This sulfur has a lone pair. The same as 2 lone pairs, gets to keep both of them.
Is it 5?
And this bond here has 2 electrons in it. How do you think those are going to get shared? Who has the higher electronegativity, sulfur or sulfur?
Equal.
They're equal, right? So they get to share that one. So how many electrons does this sulfur get to say belongs to it? So I'll call it sulfur A and sulfur B. So sulfur A gets to keep how many electrons?
4.
Plus that one.
5.
5. It gets to keep 5 because it's got 2 lone pairs and it's sharing an electron equally with another sulfur. So they each get to keep 1. If they're the same electronegativity, they get to share it equally. So that one is 5. Now what about sulfur B? How many electrons does it get to keep for itself?
3.
3. So let's figure out what the oxidation numbers should be. So oxygen should have 6 valence electrons, and we subtract the electrons that it gets to keep in the molecule. So what's the oxidation number of the first electron? Well, actually of all the electrons, of all the oxygens, they all have 8. So
-2.
They're all -2. And you will find that basically oxygen is always -2 because it gets to keep all of the electrons that it's sharing with anybody except fluorine or itself. So for instance, if it's O2, get a different color here. If it's O2, basically it's sharing electrons with itself. So they each get 6 valence electrons. So their oxidation number of oxygen there would be 0 because they're both sharing the same number of electrons. So they each have 6 valence electrons. But in this instance, when they're stealing it from someone else, And they're almost always more electronegative than everybody but fluorine. So unless oxygen's in a bond with fluorine, it gets to keep all of the shared electrons and its own electrons. So oxygen almost always is going to be -2. So this oxygen's -2, this one's -2, this one's -2. Now let's do the sulfurs. So this sulfur A has 5 valence electrons that it gets to keep for itself. And how many valence electrons does sulfur have when it's just an atom?
6.
6. So it has 6, and this one has 5. So what's its oxidation number?
1.
+1. Always put plus or minus in front of it. And then sulfur B is supposed to have 6 valence electrons, but it only has 3 that it gets to keep for itself. So what's its oxidation number?
+3.
+3, exactly. So let's add everybody up together. So we've got 3. As you can see, it's getting kind of complicated here. So let me erase some of this stuff so we can actually count them. So +1, +3. All right, so we've got 3 oxygens, and they're all -2. So that is -6. And we've got 2 sulfurs, right? One of them, this one, is +3. And what's the other one? What's the oxidation number of sulfur A? This is sulfur B, it's +3, +1. And what's my total?
4.
6, -6 +3 +1.
-2.
-2, which is the charge. So we did that right. So man, I can't believe how I remembered how thiosulfate went together. That was lucky. Yeah. So you check to make sure your formal charges. Actually, I probably should have changed that. You know, assign formal charges and oxidation numbers, and make sure you get the same number each time. So yeah. So I'll leave you with that. So remember, NO2 doesn't have a charge, so that's not nitrite ion. That's nitrogen, the mononitrogen dioxide. So this had a charge. We did that one. And so if it doesn't have a charge, you don't include extra electrons. And so how you deal up with the oxidation numbers, look at the electronegativities. If 2 atoms have the same electronegativity, they share whatever shared electrons they have, they get to share them equally. If one has more electronegativity, it gets to keep everything. And that's how you work it out. So basically, any time you see a diatomic molecule, I think one of them is F2, what's going to be the oxidation number of both those fluorines?
-2.
Actually, fluorine is almost always -1. Actually, fluorine is always -1, except in one instance. Because fluorine has 7 valence electrons, right? And it gets to keep those because it's very electronegative. And if it makes a single bond, so it gets to keep the other electron as well. So it has 7 valence electrons, it gets to keep 8, so it's -1. So it's always -1, except in one instance, when it's bound to itself. And so when it's bound to itself as F2, what's its oxidation number? Here, let me clear this and we'll figure this out. Let's just do fluorine. Let's just draw fluorine. How many valence electrons does fluorine have? 7, right? We have 2 fluorines. That's 14 electrons. And it's got a bond here. So that's 2 we get rid of. So we have 12 electrons to go around. So let's do it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's what the Lewis diagram for fluorine looks like. And that's one electron. That's another electron. So now they both have 8. They both have a complete shell. So they're both got to the happy number. How many valence electrons does fluorine have? The answer is 7 as an atom. Now the question is, how many valence electrons does it have as a molecule? How many valence electrons does that fluorine have?
Can you repeat the question again?
How many valence electrons does each fluorine have in this diagram right here? Just talking valence electrons right now.
6?
Mm-mm.
7.
7, right? It's got 2, 4, 6, 7. So if we were calculating formal charge, we'd say they have 7 as an atom and they have 7 as a molecule. So there's no formal charge, which we know fluorine F2 is there's no charge. So that makes sense. But let's do oxidation number. Now for oxidation number, we need to take into consideration the electronegativities. So who has a higher negativity, fluorine or fluorine?
Equal.
They're equal. They're exactly equal. So so they each get to keep, undo. They each get to keep their lone pairs. So they each have 6 to start with. But so then it comes down to this shared pair here. Now, remember, whoever has the higher electronegativity gets to keep all the electrons. But who has the higher electronegativity? Whose electronegativity number is greater, fluorine A or fluorine B?
The same.
They're exactly the same. So they share this. They share it equally because they're pulling on those pair of electrons as hard as each other, exactly the same. And so they share them. And so we say they have 6 lone pairs and they have 1 that they get to keep from the bond because they share it equally. So 7. So their oxidation number is 7 minus 7 equals 0. So basically anytime you see H2 or O2 or N2, it doesn't matter what it is. If it's a diatomic molecule and it's exactly the same atom, oxidation number is always 0 because whatever shared electrons they have, they share equally. So if there's no charge, there's no overall charge, so the oxidation numbers have to add up to 0. There's only 2 of them, and they're the same, so it's 0. So this is the only time fluorine doesn't have an oxidation number of -1, is when it's bound to itself. Every other time, no matter who it's bound to, it has a higher electronegativity, and it's going to keep all the shared electrons. But in this instance, it can't because it's being shared equally. Okay? So I actually gave away the answer for one of them. I figured it's
So
probably not a bad idea.
in the exam for this question, just do you want me to answer how many oxidation number?
What's the question?
Like to answer this question in the exam, I have just to draw how it's look like.
Right. So you draw the diagram, and then you say what oxidation number every atom has.
Okay. Do you
You
want me to
go around it and say what the oxidation numbers are.
Okay. Do you want me to show how I get the number of the oxidation, like how to draw and how, like what you did now?
Unless I say so, no.
Okay.
If it doesn't spell it out, you can just, I mean, I think on an exam, I would probably say show your work. If it says show your work, then you have to, yeah, you have to show the calculations. It doesn't say that specifically here.
Okay, for this fluorine, since it's not doesn't have a charge, it's gonna be the oxidation number 0.
Oh, remember, charge and oxidation are not the same thing.
Oh, okay.
So Eve, so let's look at,
No, but I mean fluorine in that case, it doesn't have oxygen atom. That's why. I thought.
no, but let's look at HF. So 1, 2, 3, 4, 5, 6. So in this instance, when it's hydrogen fluoride, the oxidation, so we know the electrons are going to move toward fluorine, right? So how many, so hydrogen normally has 1 electron, right? 1 valence electron. So from this bond, how many of those electrons does it get to keep? Who's more electronegative?
Fluorine.
Fluorine. So does hydrogen get to keep either of those shared electrons?
No.
No. So we subtract 0, so it has an oxidation number of +1. Now fluorine has 2, 4, 6, and both the shared electrons, because it's much more electronegative. So now it has 7 valence electrons as an atom, and 8 valence electrons when it keeps all of the bound electrons as well. So its oxidation number is -1, not +1, -1. That's different from charge. Notice fluorine doesn't have a charge here, and hydrogen doesn't have a charge here. There's a bond, but this means that fluorine basically is that's a very strong negative partial charge, and hydrogen is very strong positive partial charge. Doesn't mean they're charged. It means that the fluorine is going to have more of the electrons than the hydrogen does. Yeah, so oxidation numbers are different than charge. It's not the same thing. Basically, it's the charge they would have if it was an ionic compound, but it's not. It's the covalent compound. Excuse me. So, any other questions? Something just pop up in the chat. Is there a question from there? Yeah, if you have any questions on these, office hours on Thursday, or just send me an email, okay?
Okay.
Man, you sound so sad. Oh no. Don't be sad. This will all be over soon. All right, I will see you tonight. We're going to start with gas laws. Gas laws will make your head explode like this stuff does, okay? All right, I'll see you tonight at lecture.
Thank you.
All right, bye-bye.